Hi, this video is on an incredibly important skill that probably you haven't learned before in another math class or a science class, and the skill is creating equations. So how do you build equations? You've probably learned or seen equations before, and how did people come up with those things in the first place? So that is the essential question for today. How do scientists make equations? And hopefully you're also asking yourself, why would I ever want to do that? And hopefully we'll show you why. I know that equations can be like one of the scariest parts of physics. Like some people, when they picture a physics class, they picture tons and tons of equations. And so I first want to make you aware that we really are only going to be doing 10 or less equations this entire year. And each equation that we do is one we've chosen very carefully to be a powerful equation that can solve lots of different types of problems, but we don't want to overwhelm you with the number of equations. The world actually works with surprisingly few equations that can be applied in lots of different ways. And we're going to be building our equations from scratch, just like the very first scientists that ever invented these equations. There's a reason why equations look the way they do, and when you understand that, you're a much more powerful problem solver. But in case you were worried about it, we will also give you equations on tests, and of course you can always use your notes, so do jot those things down so you have those. If you were worried about memorizing a lot of things, that shouldn't be something you'll have to worry about in this class. Of course, you could always build equations again once you know how to build them as well. All right, so what does building an equation look like? What is this process? Well, the first step in the process is to identify the dependent variable and all of the independent variables it depends on. So if you think back to the experiment you did first quarter, you had something you were measuring and something you were changing, right? So the independent variables are the ones you were changing, and the dependent was the thing you're measuring. And while we only changed one independent variable, there probably are multiple variables that could have affected your dependent variable as well. A lot of you guys did things like cookie height, and you changed the baking soda, but you could have also changed the flour, changed the water, changed the temperature you cooked it at, right? So there actually sometimes are lots of independent variables that affect the same dependent variable. So you need to figure out each one of those independent variables. So for example, let's assume you want to make an equation to scientifically calculate the niceness of each of your teachers. And we're going to make this variable known as n for niceness value. You decide that the niceness of a teacher depends on only two things. You don't care about anything other than these two things. Number one, how much candy does my teacher give out in class, or the variable c, and how much homework does that a teacher assign, a variable h. So this is the first step of building the equation. We found the dependent variable, which is niceness, and the two independent variables, candy and the amount of homework assigned. The next step in building out an equation is to figure out what are the mathematical relationships between each of the dependent variables and the independent variable. And you might do a scientific experiment to figure this out, like we've done before, or sometimes it's just kind of logical that you can reason out what the relationship is. So for example, when a teacher's candy goes up, when teachers give you more candy, probably most students are going to say their niceness value is going to go up as well. So that tells me that there is a linear relationship between candy and niceness. So that's the first relationship. Then we have to consider the other variable, homework. Generally speaking, most students would say when the amount of homework a teacher assigned goes up, the niceness of the teacher goes down. And that tells me that there is an inverse relationship between h and n. So we have our dependent variable n, and we now know two different relationships of other variables, of our independent variables, with that n. Okay, so let's do the last step, the building step. You're going to build your equation, and the way you do that is you start by putting your dependent variable on one side of an equal sign. So in this case, n equals. Then all of the independent variables that have linear relationships are going to go on the numerator. So I usually draw a line on the other side, and on the numerator, which is the top, I'm putting all of my linear relationships. So there was linear between candy and niceness, because candy going up made n go up. So I put that c on the top of the fraction on the other side. And then I put any inverse relationships on the denominator, or the bottom of the other side. Incidentally, if you had more than one linear relationship or more than one inverse relationship, you can just add more variables to that top or bottom of the fraction. They're multiplying them all together is what we're doing, c times whatever else. So if you decided that niceness also was stickers given out, At S, we could put C times S on the top, and then we'd still have our H on the bottom. So you can add as many variables as you need, but all the linear ones go on the top, and all the inverse ones go on the bottom. So we've showed you how to do something, but let's now talk about why it works so you really understand these equations at a deeper level. The big idea with an equation is that the values on each side are always balanced. So if you have an easy equation like 1 plus 2 equals 3, we have the same amount on one side, the 1 plus 2, as we have on the other side, the 3. And if we make one side bigger, like if we double, we put a 2 times on one side, right? Then we have to do the same thing to the other side to keep it balanced. So anytime one variable changes, it's going to impact other variables in the equation. And the same thing is going to be true with this equation that we built. So if we start with that equation, the C over H, and we make C bigger, so we have a teacher that is now going to give more candy. And we're not going to change the homework, same amount of homework, but we're going to make that C bigger. So what we've done is we've made this whole side of the equation a bigger value, right? We've multiplied the whole side of the equation. We've made it bigger. And if we double the amount of candy, this whole side of the equation is going to be twice as big as well. C over H is 2 times as much as it was before. And so if you think about the other side of the equation, what do we have to have happen to n in order to keep this equation balanced? N has to go bigger as well. N is going to have to double to keep up with C. So this is why linear relationships belong on the top of the fraction, because if you double the top of a fraction, you double the value of the fraction. That's going to make the other side of the equation bigger by the same ratio. Okay, now let's look at building equations from the perspective of the inverse relationships. Again, we have to keep the values on the two sides balanced, and so if one of the variables changes, the other side of the equation is going to have to change as well. So this time, if we make H a bigger value, more homework, but the same amount of candy. So this was, we're not changing the C now, we're just changing the amount of homework. Well, we're dividing by a bigger number. And if you picture taking pizza and dividing it by more and more people, right, each person is going to get less and less and less. So the bigger the value we're dividing by, the smaller the value that we have. And so on the other side of the equal sign, the bigger H gets, the more parts we're dividing C into, the smaller the n value is going to get as well. So my equation compensates for itself just in the way we were expecting inverse relationships to work. When one variable gets bigger, the other gets smaller, and vice versa. So as I said at the beginning, hopefully anytime a teacher asks you to learn something, you're thinking to yourself, why would I ever want to do this? Is this just some hoop the teacher is making me jump through? Hopefully teachers can always answer that question, but especially this year when our learning is so limited because we're at home, we're only teaching you things that are really, really crucial. But why do you want to learn how to write an equation? Well, equations are really shortcuts in the world. They let you do things much, much faster. They save us a ton of time, and hopefully in your life you would like to save time. Because when you have lots of variables changing at the same time, it takes a long time to figure out how each one affects the dependent variable. It would take you a long time to do that math. But if you can just have an equation where you can stuff them all in at once, it lets you figure out the total impact of these changes with a single calculation instead of having to calculate each change and how it affects the thing that you're curious about. A second reason that equations are super powerful is that once you understand how to build an equation, you can take an equation and break it out into the relationships, and then you can understand the way the world works just by taking an existing equation and figuring out what this must mean. One of the most famous equations out there is known as the universal law of gravitation. And this equation, understanding this equation is the reason why our astronauts can go to the moon. There was a launch of a SpaceX rocket into orbit the other day, which we definitely could not have done without understanding the universal law of gravitation. So it sounds like it'll be a big, scary equation, and it's bigger than most of the equations we've used in our class, but it's still pretty straightforward, and there's nothing too complicated about the relationships. And what you'll see here is this F stands for the force of gravity, which is a force you probably already know, and you'll see in this equation that the force of gravity has two linear relationships. It is related to something called m1, which is the mass of an object, and m2, which is a mass of another object. So for gravity, it's like this is the mass of you and this is the mass of the planet that you're interested in. And those are both going to be linear relationships because they are on the top of the fraction and we are multiplying by them. We'll see also that there is an inverse relationship shown in the universal law of gravitation, and that is distance which is basically the distance between the two objects. So the force of gravity acting on you has an inverse relationship with the distance between you. It's a little bit of a complicated inverse relationship. It's distance squared, which changes something slightly, but that doesn't change the fact that it's an inverse relationship. There is one more thing in this equation that probably stands out, and that is this big G. G is a constant. It's just a number. It's like 4, 12. It's a bigger number than that, but it doesn't belong on the top or the bottom of the fraction because it's not really a relationship because it's never changing. G is always the same value. So anyway, if you're given this equation, you now can understand something more about the way gravitation works just because you know that all the linear relationships belong on the top and the inverse relationships belong on the bottom. Okay, so hopefully now you are able to understand how scientists make equations, and you have a sense of why we're asking you to learn this important skill. I've also thrown a nice Calvin and Hobbes comic at you to reward you for getting through the video. Thanks for your time.